Hello everyone, welcome to my poster presentation. I am presenting my poster entitled A Framework for Massively Parallel Simulation of FSI Problems. Multiphysics problems can be found everywhere around us. A good example is conjugate transfer when heat is transferred from one resource to the other one. Or another example, which is a subject of our research in the current work, is the simulation of blood flow inside a human aorta. There are generally two categories of methods to solve multiphysics problems, monolithic methods and partition methods. In the monolithic methods, all equations from different physics are discretized and solved together, but in partition methods, the problems are decomposed into smaller problems according to the current physics, and they are treated independently. In the current work, we follow a partitioned approach in which we decompose the problem into smaller subdomains, and then we can use well-adapted solvers for each domain, but we need a coupling method to couple these two solvers to each other. Using partitioned approach provides us great opportunity because we can use different solvers, different numerical methods, but there are some issues that must be addressed. Intercode data communication, boundary data mapping in case of non-matching meshes, equation coupling at the boundaries, and intercode load balancing are the most important issues that must be addressed. For our solver, we use two instances of thermofluids code as fluid solver and solid solver, and we use precise library to couple these two solvers to each other. To efficiently exploit the available compute resources, we exploit different levels of parallelization. First of all, inside each single physics solver, we decompose the problem into smaller sub-partitions and assign them into different CPUs. The communication between different CPUs of each solver is done in a fully point-to-point scheme. Also, the communication between the boundary CPUs from both solvers are also done in a point-to-point way, which increase the performance over code. Inside each CPU, we follow SIMD instructions. The communication initialization is also done in a parallel way, and for coupling at the boundaries, we use a parallel semi-implicit strategy with an advanced Kaiser-Newton scheme. We need a database. We use a database load balancing scheme for inter-solver load balancing. The purpose is to efficiently divide the available resources between the solvers. We have fixed amount of compute resources, say CPUs, and we need to divide them efficiently between the different solvers. We follow a two-steps approach. At the first step, we create a performance model for each solver, and then in the second step, we use this performance model to optimize this resource distribution. For performance modeling, we do some small simulations and we gather the performance data, we check different models, we evaluate them, and then we choose the best model. And after creating these performance models, we have an optimizer, an integer optimizer, which compares the runtimes and assigns appropriate number of compute resources to each solver. For details, please refer to our poster and the other papers that we have cited in our poster. Okay, I present the scalability, strong scalability results for a patient-specific aorta test case. We use unstructured tetrahedral mesh for both fluid and solid. And we run the scalability test on SuperMOOC NG supercomputer at LRZ Supercomputing Center in Garching, Germany. As you can see in this graph, we achieved a very good scalability up to 11,520 cores with 85% parallel efficiency, which proves the effectiveness and effectiveness of our implemented effectiveness and efficiency of our implemented methods. That was it. So please do not hesitate to contact me if you have any question regarding the details. At the end, I would like to use this opportunity to thank ISC Group and their sponsors and media sponsors that provided us this opportunity to present our research. Thank you very much for your attention.